Hi again, everyone, and welcome to the day 2 of the 2026 Annual LiDAR EFI Cross-Country Checkup. Today's workshop is titled Deep Learning with Airborne Laser Scanning Data for Forest Inventories. My name is Sharon Yang, and I'm with the Canadian Institute of Forestry. We'll be providing the Zoom platform and technical support for this workshop. I will now pass it over to Brent Murray, PhD candidate with the Integrated Remote Sensing Studio at the University of British Columbia, to kick off today's workshop. Over to you, Brent.
Hi, everybody, and good morning or good afternoon to those who are on the other coast from us. I just wanted to welcome you all to this workshop as well, and I am very excited to be sharing some of this knowledge with you and just go forward through this tutorial about how to use deep learning with airborne laser scanning data for forest inventories, because I think it's such an important topic. So I just wanted to introduce the team that has worked on this project, and also who are going to be instructing today. And I'll get each of them to introduce themselves a little bit. But first of all, again, my name is Brent Murray. I'm a PhD candidate in the Integrated Remote Sensing Studio under the supervision of Dr. Nicholas Coops. And my project is mainly focused on using deep learning and data fusion techniques to estimate tree species. Again, I'm excited to be part of this workshop. I'll pass it over to Harry to introduce himself.
Yeah, so my name's Harry Seeley. I work with Brent in the Integrated Remote Sensing Studio here at UBC. My project is similar to Brent's, but I'm focused on estimating forest above ground biomass components directly from airborne laser scanning data. I'll pass it to you, Abe.
Hi, everyone. I'm working with Brent and Harry in IRSS as a postdoc researcher, and now I'm also working on the tree species composition estimation using airborne LiDAR and sentinel imagery and the transferability of deep learning networks. And yeah, that's all. And I will pass to Hammond.
Yes, hello everyone. My name is Ahmed Rajab. I am lead AI scientist working for Calmet Energy in the RIN, Natural Resources Canada. I'm also an adjunct professor at Polytechnique Montreal and member of Mila Quebec AI Institute. I'm leading the development of AI-based tools for at Natural Resources Canada in close collaboration with CFS and UBC on enhancing forest inventory. And nice to be with you today. I'll pass it
Perfect.
to
Nicholas, unfortunately, is not here at this point in time, but I'll just introduce him. He is the head PI of the Integrated Remote Sensing Studio, and he is mine and Harry's PhD supervisors, and he is also working with UA on these projects as well. So again, thank you so much for everybody for attending this workshop. I'm just going to quickly go over some of the, just an overview of this workshop, how we expect this to kind of run, and how we want you to also engage with us throughout this workshop. So a quick overview is that this is a very introductory workshop for how deep learning techniques work for enhanced forest inventories. So we're going to go over things like some basic terminology, how to train deep learning models, how to prepare the data for that training, and also how to evaluate and deploy these different models as well, so that we can get these estimates of different forest attributes. So some things that we're hoping that you learn is some basic concepts of deep learning, how to prepare and read in data, the basics uses of PyTorch, which is the library that we are using for deep learning in this workshop. Also, just how to train these deep learning models for specifically species classification and biomass prediction tasks, and then also to test and evaluate these deep learning models. So how this tutorial is set up is, again, a very introductory tutorial on how to implement this. And with this in mind, we want you to follow along with what we see on the website, and I will post that in the chat now. This website has all of the information that we are going to be presenting throughout this tutorial, and we want you to follow along with what we are talking about. This website will remain open after the workshop for you to review any content, to share it with others, and you're more than welcome to clone this repo as well, as it serves as sort of a launching point for a lot of these EFI deep learning projects. So again, we encourage you to follow along, ask questions, and yeah, be engaged with this tutorial. One of the biggest things when we go into these coding tutorials or workshops is that we often get lost in the code. We can't pay attention because it's going so fast. We get lost. We can't set up things. So what we really want you to do is focus on the theory and concepts and the workflows that we are going to be explaining, and then use the code that is provided on the website later as a reference to reinforce what you've learned. If something isn't clear, we want you to ask questions in the chat box or in the question and answer panel. And after the workshop, you can also ask us questions through GitHub. And all of that information is going to be on the website. So how to follow along? Again, follow along with these broad concepts. If you want to implement this code later, there is a source folder on the GitHub page. That way you can use that code to implement this into your own workflows. And then we've additionally provided all of the data and the outputs for you so you can enjoy the workshop without having to worry about coding at the same time. So again, be curious and ask questions. Whoever's not presenting at that time is going to be monitoring the chat box. So please make sure that you are asking those questions. And again, after the workshop, you can submit an issue or a question via GitHub. And if you notice on the right-hand side of the tutorial website, you're going to see that there's a report an issue button. If you hit that, it's going to take you straight to that to the site where you can report an issue, and we will monitor those questions there as well. So as we go into this, I just wanted to also introduce the idea of this human-centric AI. And I don't think there's a better person to do that than Ahmed Ragab here. And I just wanted to pass that over to him so that he can start us off with how this human-centric AI works and the importance of the humans in the process of deep learning.
Thank you very much, Brent. Yeah, thank you very much, Brent, for that introduction and for getting the stage set. Before we get started, I want to sincerely thank Harry, Brent, Yue, and Professor Nicholas Coe. It's a pleasure to be here to showcase how deep learning and AI can truly transform enhanced forest inventory. And this work is a result of long-standing collaboration that began in 2022 between Canmet Energy of Natural Resources Canada and Professor Nicholas' team at UBC, Harry, Brent, and the Canadian Forest Service, working closely with Joanne White and Adam Dick. And our focus has been on applying in advanced deep learning to estimate the above ground biomass and tree species composition. And we are proud to continue this fruitful partnership today. And we are particularly excited to show how deep learning, when applied to the right forestry challenges, become powerful tool for domain experts. And thank you all for the initiative and integrate our collective thoughts into this tutorial. I hope you'll find it useful. Here's a quick overview on what we will cover in this section. And firstly, we'll frame how human-centric AI and its role in forest inventory. Then we'll look at the 4 pillars of AI capabilities in forestry. After that, we'll go through each modeling types in more details, and at each step, we will highlight not only what AI does, but also where human expertise remain essential. So, as we kick off this cross-country checkup yesterday, and this is the second day focusing on the deep learning, we want to talk about the fundamental shift in how we approach enhancing forest inventory through the different capabilities of AI. As you all know, forestry has always been built on solid foundations. We have field measurements, algometric equations, statistical models. They are not just legacy methods. They are the heart, of what we do. However, data landscape has shifted, and the richness of the airborne laser scanning and the multispectral imagery, we can now observe forest structure at a level of details that simply was not possible before. And in this setting, artificial intelligence, especially deep learning, should not be viewed as the replacement of forestry expertise. Instead, think of it as human-centric tools that extend our reach. Deep learning and AI amplifies our decision-making rather than automating it away. From data preparation, model interpretation, human judgment remains the governor of the workflow. And to frame our discussion today, we have broken down the AI modeling capabilities in 4 pillars: predictive, descriptive, prescriptive, and generative. So the key takeaway here is that AI never operates in a vacuum. As you see on the right side of this table, each modeling capability has an indispensable role of the human. In descriptive work, humans define what's meaningful patterns, structures actually look like across the diverse ecosystems. In predictive tasks, we decide which plots are trustworthy and representative. And we move into prescriptive and generative realm. So our thoughts becomes even more critical, and the human expertise is critical to ensure that AI recommendations align with policy, biodiversity goal, and ecological realism. This framing helps us to see deep learning as part of broader human-guided system, not black box. Let's look at the first pillar, which is descriptive modeling. This is where we learn pattern structure from data. Traditionally, we summarized ALS point clouds using handcrafted metrics through like height percentiles or canopy cover. And deep learning allowed us to move past these manual definitions. It learns hierarchical feature representative directly from the raw data. And this means that the model can capture nonlinear patterns in both vertical and horizontal complexity that are incredibly difficult to define by hand. For EFI, this results in more consistent representations across different regions. But again, the expert eye is essential here to choose the right data and to ensure patterns generated by the model sees actually makes sense from silviculture and other perspectives. The second pillar, which is a predictive model, is likely the most familiar to everyone here. This is the workhouse. And this is actually the, when we use the inputs like ALS LiDAR to estimate the different attributes like biomass, volume, or species composition. So this is actually what most of the people hear about these days. I want to pause here to clear up the major misconception. When people hear AI today, they often think of ChatGPT or large language model, and there is a common impression that all AI is massive black box APIs that consume huge amount of energy. That's not the AI we use for enhanced forest inventory. Our models are task-specific modeling approach. Unlike ChatGPT, which tries to know everything about everything, our models are optimized solely on forest attributes. They are computationally efficient, lightweight, and can often run on a single workstation. We are not building chatbots. We are building precise and energy-conscious scientific tools for forestry. So the third pillar is the prescriptive modeling, which takes us from what is there to what should we do. While this workshop doesn't focus on prescriptive models directly, they are very relevant forestry application. They can support management planning, help prioritize harvesting or conservation, also guide decision about sampling or data acquisition. The logic is simple. Better EFI predictions leads to better forestry decision. But we need domain expertise to ensure these recommendations are practical, actionable, and stay aligned with our long-term forest management objectives. This is where the model stop and the forester take over. So finally, we have the frontier, generative modeling. This is about exploring what-if scenarios. But by using this powerful specialized modeling approach, we can simulate forest structures under different climate trajectories or disturbance regimes. It allows us to augment our data synthesizing realistic forest structure or remote regions where field plots are sparse or while remaining computationally lean. So as we close, I want to leave you with this deep learning is a trajectory, not a destination. It's powerful modeling approach that we placed in the hand of experts, allow us to move forward a digital twin of our forests that's not only accurate, but also ecologically sound and resource efficient. With that, I will give the floor to these three smart guys to dive deeply into the realm of the deep learning and show how these tools work in practice. Thank you.
This workshop is very focused on the concepts of deep learning and the workflows that are associated to deep learning for enhanced forest inventories. This workshop doesn't go into too much detail on how to set up your specific environments or how to set up your machines in order to do this. It is a workflow for how to implement these into your current workflows. Setting that up within your specific environments or within your specific companies is going to differ from place to place based on the security protocols that you have in these areas. Before we dive into data preparation and training our models, I just wanted to give a brief overview of what deep learning is and how that ties into enhanced forest inventories, because we've heard all of these terms throughout social media or online or in the news, and I just wanted to clear up some of those common misconceptions and just start us all off on the same level so that way we can implement these terms throughout the rest of our workshop. So an overview of this quick section is we're going to provide an introduction to the deep learning concepts and how they are applied to enhanced forest inventories, again, with the concept of this human-centric AI. So by the end of this section, I'm hoping that you will all be able to explain the role of AI and deep learning within an enhanced forest model, distinguish the differences between AI, machine learning, and deep learning, describe the different structures of the deep neural networks, explain how models learn, compare image-based, which is a very common deep learning task, versus point-based deep learning, which is what we are going to be focusing on since EFIs are predominantly using LiDAR-based data, the core of deep learning terminology, and also recognize common forestry-specific challenges that we see within this realm. So starting off broad, what is deep learning? So deep learning is a branch of machine learning, which is then a branch of AI. And so AI is a system that mimics human decision making. And those are things like knowledge bases or rule-based classifications. Machine learning, on the other hand, is a subset of that AI, which improves learning through data-driven experience. And these are some of the common examples of this would be random forests or support vector machines, which I'm sure many of you have already used for your different workflows. Deep learning, on the other hand, is a subset of machine learning, which uses neural networks with many different hidden layers within them. And this is why they are called deep learning models or deep neural networks, because they have many different hidden layers in them. And some common approaches with this are convolutional neural networks or CNNs, transformers, graph neural networks, and so on. So some key concepts with neural networks, and here are some of the key components that we talk about within these different models. So we have these layers, and these are the hidden components of these neural networks that we don't really get to see. So we have our inputs and we have our outputs, and we can understand those, but the stuff that's in the middle are these hidden layers. And these layers are made up of different components, and they are called neurons. And so the width of our layer is based on how many neurons we have within that component. And in that black box that we see that's described with layer, we have 6 neurons that are associated to that. And there's connections between each and every one of the inputs that comes before and after. And those connections are called weights. The depth is the number of layers that we see within our networks. And in this case, we have 5 specific layers in our network. So as we increase the depth and the width of our networks, we also increase the representational power that we are able to extract from these inputs in order to meet what our output is supposed to be. But with the increase of this depth and width, we also increase the computational demand and the risk of overfitting within our model. So trying to find the most optimal approach for our specific purpose is really dependent upon the data that we're using and the task that we're trying to achieve. So I've already briefly mentioned a neuron, and a neuron is the most fundamental part of a neural network. And this is where the learning basically happens. And so what happens is that we have this input or a set of inputs, and we weight those to produce some sort of output. And that output is changed based on the bias. And these weights and biases that we have within these neurons are learned throughout the training process, which I'm going to talk about in a little bit. An additional component to this neuron is what's called an activation function. And this introduces nonlinearity into the model so that way we can learn complex relationships. And just as a note, there are many different types of activation functions, and you are encouraged to do research onto which one would be best used for your specific use case. And that's not part of this workshop here, but just keep that in mind as we move forward. So how do neural networks learn? It's through this prediction feedback loop where we have this iterative approach where we predict some sort of variable. We then assess that. The assessment provides feedback to the model and it adjusts those weights and biases. And that's all driven by the goal, the task, and the data. So the goal is often what we define as the loss function. We're trying to minimize the error that we see within our models. And this loss function, again, is dependent on the task at hand. And so as you can see in the figure in the bottom, we are trying to minimize that loss. We are trying to make those 2 validation and training losses minimized throughout multiple epochs. And an epoch is related to 1 full pass of the training data that we provide. The gradients, on the other hand, are the sensitivity of the different small changes that we see within these weights and biases, and I'm going to explain that a little bit further later on. So some common deep learning tasks that we have within, especially within forestry related aspects are classification, regression, and segmentation. So classification, these are things like tree species mapping, land cover classification, disturbance detection. So in this case, very simple case on the bottom, we have an image of a tree. We apply some sort of convolution or some filters to that, and then we classify this as pine. Regression, on the other hand, this can be things like measuring above ground biomass, canopy cover, tree height, crown size, things like that. And what that does is we, again, have this image on as our input. We apply these convolutions, and then we get some sort of estimate of above ground biomass. Segmentation, on the other hand, is the goal of this is to assign labels to every pixel or point. So in a case like this, we have tree crown delineation, stand boundaries, structural mapping, things like that. And we're trying to understand where the specific components of this image are related to the tree, for example. So the data component of this is also an extremely important part of deep learning models or deep neural networks. And this learning happens through the patterns identified in the data. And so in deep learning, we often have three distinct data sets. The training data, which allows us to learn these patterns and these different parameters. We have the validation data, which allows us to tune our hyperparameters and prevent overfitting so we can understand what's going on as we apply these models. And then we finally have a testing data set as well, which is a final unbiased performance estimate. And it is very important to note that we never mix any of these training samples, validation samples, or testing samples together, as this causes misleading performances and metrics and just generalizes our models very, very poorly. So it's important that these never mix throughout our training and validation process. Now I wanted to talk a little bit more about these two different kinds of deep learning approaches. And so within remote sensing, we often see image-based and point-based methods. So image-based deep learning operates typically on raster imagery, so common inputs like RGB imagery, multispectral or hyperspectral data, and this learns spatial patterns and textures within these networks. So as we can see in this figure on the bottom, these initial layers, the ones with right after the input, they learn these basic structural patterns or spatial patterns within this data. So things like straight lines. As we move further and further throughout this network, we can start to identify corners or edges or diagonals, and then we can, at the end of it, start to extract objects. So here's these tree crowns as an example. So again, a common image-based network is called a convolutional neural network, which I'm sure all of you have heard of. This is one of the core image-based architectures within deep learning. And what this does is we provide these sliding filters or kernels that iterate through the entire image, and it detects things like edges, textures, and objects. And as it goes through that different training data, we can understand these different higher representational information. Point-based deep learning, on the other hand, doesn't work with regular grid structures. So we can work with these irregular point clouds that we see within commonly within enhanced forest inventories. So it operates directly on these point clouds instead of having to extract the structural information through pixel metrics and things like that. So it learns these different spatial representations and the different weighting of these different points within these networks at again, a higher representational power as we move forward throughout this network. So a common point-based model is called set abstraction, which was first described in the PointNet++ algorithm. And what this does is it just groups nearby points, and it learns the local geometry and shape by subsampling these different points that are within this point cloud. As you can see in the bottom, we have a point cloud of a tree. We sample that based on this radius, and then we provide it to a deep neural network called PointNet. And then as we do that, we can extract further information through these smaller subsampling groups. So that way we can get this global representation of these trees with much finer detail. Going into some of the core terminology now, this is an important step before we move into how to actually train these models, because we're going to be using some of these terminology throughout the rest of this workshop. So we have things called hyperparameters and parameters. And so parameters are those learned values, those weights and biases that we see within these networks. And these are what are trained throughout the model. The hyperparameters, on the other hand, are these user-defined variables such as the learning rate, batch size, epoch, and model depth, which I will talk a little bit more about these in a little bit. But these are user-defined parameters that are important to set before we start training our models. And we can do things like hyperparameter tuning to understand which are these optimal variables for this. But don't forget that these are human-defined variables, so that way we can influence what we are seeing within our networks. We also have inputs, labels, and learned features. So these input features are what the model sees. This is the data that we are providing. Associated to that, we also have the labels, which are what we're trying to predict. So each of these samples that we provide has an associated label to it, whether that's a species class or a biomass variable, or a segmentation label as well. We can provide that to the model so that we can understand what our model is learning. We also have these learned features, which are these internal representations or these weights and biases that are inside of these features, and we can use that to help distinguish different clusters of these learned features to make sure that our models are learning correctly. We also have logits, which are our outputs of our final model. So these are the final variables that we see within this. In a classification example, these are often the probability of this sample belonging to a specific class. Data augmentation is another very important term to just define. We're not specifically doing data augmentation within this workshop, but you probably have heard of this. And basically what this does is it's artificially increasing the training diversity that we see within our models. Often because in forestry related context, we don't have enough data to provide our models to learn these different variability that we see within these point clouds. So on the example on the right-hand side here, we have this input point cloud, and then we remove some points, maybe we then add some noise to it, and then we can rotate those point clouds as well to provide our models with a different kind of representation of what's going on within these forest structures. And this is very important, especially when we have limited labeled data sets like we often do within forestry contexts. We have batches and batch size. So when we train our models, we can't just provide it all of our data. Deep learning models often require thousands upon thousands of different samples to learn these different representations. So we can't just provide the model with all of our data. So we have these small subsets called batches that we provide our model so that it can learn these different representations. And the size of these batches is a hyperparameter that we use. And this is the samples that we use at each different training set. So we have architecture and weights as well. So the architecture is the model network structure, and this is a fixed thing that we provide in there. That's related to the number of layers, how many neurons, and how these connect. We also have the weights, again, which are these learned numerical value, which changes throughout the training process. You might have also heard of a training loop, which is related back to the prediction feedback loop. This repeated forward pass is where we predict, then we compute our loss, which is the assessment. We then have a backward pass, which is our feedback, and then a parameter update, which is our adjust. So this is something that we can, how we train these different models. We also have this thing called transfer learning and fine tuning, which is very common within forestry due to the limited data that we have. So transfer learning starts from a pre-trained model and we apply that to our specific use case. We have an area that has this same type of species in one, we train a model on that, and we apply it to another area which has the same species. If we want to introduce more species or different species into our model, we can use what's called fine-tuning to adapt the different weights that we see within our network to apply to these different species. We also have some common challenges within deep learning and forestry. We often see sensor and site variability, like what I just said, and this often impacts the generalization that we have within these models. And so we can fine tune or adapt to our models to these specific domains. We also often have spatial autocorrelation, which inflates our accuracy of our models. So we can introduce different subsampling strategies into our models so we can reduce the amount of spatial autocorrelation that we see within these data sets. We also often have class imbalance in these real world examples, and this often impacts we have a bias towards the majority classes, where the minority classes are just not being predicted at a high level of accuracy. So with these things, we can often introduce class weighting or different loss designs to mitigate some of these issues. Often within deep learning as well, we often see these models trained and developed on these synthetic benchmarks. And now these synthetic benchmarks aren't a bad thing, but it often limits how we can transfer these to real world applications. And so often we have to adapt to these different approaches based on the area that we're looking at or the different types of data sets that we're using. So we have to increase the network's depth or the width or change the loss function, things like that. So that way we can actually represent what we're seeing in the real world. Finally, we also have very limited labels often. We don't have enough training data or validation data that is field validated and sampled throughout this entire process. And it just reduced the robustness of these models. Again, deep learning models need a ton of data in order to learn the different variability patterns that we see within these data sets. And so often we need to do things like augmentation or transfer learning or pseudo data generation. So that way we can understand these different approaches that we see within this. That was a lot of information. But I just wanted to leave everybody off with this, is that human expertise is essential in AI-driven forest inventories. The models don't define the objectives. They don't validate our data. We need to have this forestry knowledge to select the appropriate data to assess these models and to also interpret the results to ensure that the decision making is being done appropriately. So again, we cannot remove the human component from these models. We have to involve the human inside of these models so that way we can understand what's going on here. That is all for this portion of the workshop. I'm going to pass it over to Harry now, who is going to talk a little bit more about the data preparation that we see within these models.
Okay, great. Thank you so much, Brent. It is a broad topic and a lot to digest. I saw the message in the general chat there, and yes, this is you don't necessarily need higher education to understand these concepts, and there's a lot of fantastic resources online that you can look at as well to learn more about deep learning and AI. Okay, so as Brent mentioned, the data pre-processing is a really critical step in a deep learning workflow, simply because deep neural networks are highly sensitive to the input data. So we're going to provide a little bit of background in this section on the pre-processing that is specific to deep learning applications in an EFI. Okay, so the study area we have, we're working with in this tutorial is the Petawawa Research Forest. If you were in the webinar from yesterday, you would have seen Dr. Joanne White present about the Petawawa Research Forest potential for use in benchmarking different EFI models. I think that's an excellent segue into this section. So I'm just going to explain a little bit on the background of the study area before we get into the workshop here. If you are interested in reproducing any of the methods in this workshop, you're welcome to do that in your own time, but due to the fact that running this code is quite computationally intensive, I don't encourage you, as Brent said, to try to follow along in real time, but rather you can look at the code and then after the workshop, you can try to implement these methods or adapt them to your own workflow. For later on, if you are interested in working with this data, you can download it at this link here. There's a Zenodo page where you can download all of the input data sets. Or if you're interested in actually running the pre-processing yourself, the original LiDAR and field plot data from the Petawawa Research Forest are provided on the National Forest Information System at these links here. So this pre-processing tutorial is mainly focused on setting the data up for a deep learning workflow. This is not a LiDAR pre-processing tutorial. Where the LiDAR package was mentioned several times in the webinar series yesterday. This has now become a core component of the EFI LiDAR processing workflow, especially in Canada. But we're not going to go into a lot of the specifics of LiDAR pre-processing in this tutorial. So if you're more interested in this, I highly encourage you to check out the LiDAR book and package documentation that are linked here. So as I mentioned, we're working with the Petawawa Research Forest data set in this tutorial. This is the oldest research forest in Canada, established in 1918. As Dr. Joanne White mentioned yesterday, this is part of the International GeoTrees Network and is a remote sensing super site. I think this might be the most comprehensive collection of forest inventory data and remote sensing data in Canada. We have multi-temporal LiDAR and multiple different plot sampling efforts to draw from. In this case, we're working with the ALS data and sample plot data that was collected in 2018. And this data set is also summarized in more detail in this paper from 2019 by White et al. If you're following along on your computer, your laptop, your desktop, I encourage you you're welcome to just follow me along on the screen here, but you could also open up the website in your own browser using that link that Brent set in the chat earlier. That might make more sense. I see somebody has their hand raised. Perhaps you could just send your question in the chat there, and then Brent or Yue can potentially answer it. Okay, so moving on here, a couple key important facts about this data set. We have 249 sample plots. These are fixed area plots with a 14.1 meter radius. All live trees with a DBH greater than 9 centimeters were measured, and the ALS data has a point density of 35 points per meter squared. So much of the LiDAR and plot data pre-processing workflow is actually similar to what we would do with a more conventional EFI approach, where I've broken this down into these sort of 7 steps here. So we'll start talking a little bit about LiDAR pre-processing, then we'll look at cleaning up the sample plot data, determining our 2 different response variables, which in this tutorial are classifying dominant tree species type as either coniferous, deciduous, or mixed, and then regressing total above ground biomass. We will then split these data sets into training, validation, and tests, like what Brent mentioned in the introduction there. We'll do some Z-score normalization, which I'll get into later, and then we'll describe the exported, sort of finalized pre-processed data products. So as I said here, we're going to focus on the high-level concepts in this tutorial, but if you are an avid R programmer and you're interested in what's going on under the hood here, you can unfold these different code chunks and see the detailed low-level code and what's going on there. And yeah, you're welcome to sort of run this in your own time. We're going to be working with a couple different R packages. If you are an R programmer, these might all be familiar to you, but we're working with one package in particular that might be less familiar, and this is the reticulate package, which just allows for interfacing between R and Python. More details provided at this link here. If you are interested in reproducing this in your own time, we do provide Python environment setup instructions that are linked here, or if you go on the setup page of the tutorial, that's provided in the home page. Yeah, as Brent said, everyone's workflows and machines and setups are going to be different, so this isn't necessarily a cookie cutter approach, and you may have to adapt it to your own situation. Okay, so here we have a nice interactive map of the Petawawa Research Forest. We have our 249 sample plots in red here, and then the LiDAR tiles spanning the research area. This is a fairly small research forest, but it is well suited for this demo tutorial. So starting off with the LiDAR pre-processing here, we have this flow chart that sort of summarizes a really high-level standard LiDAR pre-processing workflow for an EFI. We start with flying the LiDAR. We have our sort of full acquisition spanning our study area. Then we might do some noise removal, remove outlier points. We perform ground classification. Then we derive a digital elevation model. We perform height normalization. And then in the standard workflow, from that height normalized point cloud data, we would then derive LiDAR metrics like mean height, 95th height percentile. Many of these were mentioned in the webinar yesterday. And then we would plug those into our conventional modeling approach, whether it's multiple linear regression or random forest or some other parametric or non-parametric approach. In the context of deep learning, we actually skip this LiDAR metric derivation step and we plug the data right into the deep neural network. So we're going to cover some of the bits of pre-processing that occur in this sort of final step here before the data goes into the deep learning model. So there's a lot of text here summarizing this pre-processing workflow in more depth. I'm not going to go into this in too much detail, but if you are interested in the specifics, you can read up on this. The one step I will go into more detail on is this step number 4 here, normalizing the point cloud data. So normally with LiDAR point cloud data, you would have your Z coordinates, which is height above ground, and then your X and Y coordinates. The X and Y coordinates would normally be in the geographic reference system units. So this might be UTM units, and these are meters. In the context of a deep learning approach, you want to normalize these X and Y coordinates to the center of the point cloud, right? So each point cloud is its own individual local coordinate system. And this approach is sort of pioneered by early research by these authors who developed this PointNet paper back in 2017. So if you're more interested in the specific methods, you can check that out. But we're going to show an example of that later on here. So here I just outline this pre-processing pipeline at a higher level here. We're loading in a LAS catalog using the LiDAR package. We are extracting the corresponding point cloud that's associated with each individual sample plot. Then we provide some additional LiDAR pre-processing, including removing any remaining outlier points. We export these point clouds in LAS file format for use in LiDAR metric derivation for separate random forest modeling that we do for comparison later on in the tutorial. And then importantly, we remove all of the contextual LiDAR information like the coordinate system, and then we convert this point cloud to a sort of bare bones matrix that just includes the XYZ coordinates, because this is really all the deep learning model needs in terms of information. You can provide additional LiDAR attributes like intensity or return number to provide additional context, but for the purpose of this tutorial, we're just going to use XYZ coordinates. We also extract the 95th height percentile to sort of compare the plot level measurements with the LiDAR to ensure there's good alignment between those two. And then finally, we're going to export these pre-processed point clouds into a NumPy file format, which is just a Python-specific file format that allows for faster reading of the data into the deep neural network so we can accelerate training time. So before I was talking about normalizing the point cloud, and this interactive plot sort of shows an example of that. From a sort of side profile here, we can see that this particular point cloud has a canopy height of about 15 meters. And when I was talking about the XY coordinates, we can see that they're relative to plot center. So the very center of the plot has XY of about 0, 0. And then we can see they extend to plus and minus about 15 meters on either side of the plot. So that's what I mean by this normalized plot center point cloud. We can see a grid here that shows the general sort of structural patterns across the entire Petawawa data set here with the 249 point clouds shown. So just looking at this zoomed out perspective gives us an idea of how the deep neural network will be extracting different patterns from these point clouds that are related to both dominant species type and biomass. So moving on to pre-processing the sample plot data, we have individual tree measurements taken from the Petawawa Research Forest sample plots stored in this Excel spreadsheet. And in this table, we can see what some of those measurements are. So we have the plot ID, we have height measurements, DVH, species name, etc. So just to get a better idea of this data set, we've done a little examination here of the species composition. We can see that the dominant species include white pine, balsam fir, red maple, among about 20 other dominant species. Then we can move along to sort of checking alignment between the LiDAR and plot data. I think this is a really good sanity check when pre-processing LiDAR data. And so here what we're doing is we have the 95th height percentile extracted from the plot level tree measurements with tree heights taken using a vertex device. And then we have the 95th height percentile taken from all of the points within that plot. Now we can see that there are a few outlier plots, but generally there is a strong linear relationship between these two measurements, indicating that there is good relationship between the LiDAR data and plot data. And as I said, this is particularly important in this deep learning context where the model is very, very sensitive to input training data. Okay, so moving on to determining dominant species type. There are many different ways we could classify this, perhaps by basal area. But in this case, we are defining dominant species type using the total volume, which was an attribute that was already included in the tree level measurements of the PRF data. So we basically set the thresholds to be if a plot has greater than 70% deciduous volume, it is a deciduous plot, the inverse being true for coniferous. And if there is less than 30% dominance, then it is mixed, as shown in these sort of rules here. So visualizing this distribution, we can see that we primarily have a conifer-dominated data set here, with a small subset of the plots being mixed and then a smaller set being deciduous dominant. So this raises an important issue, which is common in deep learning applications in forestry, called class imbalance, which can basically lead to models that generate predictions that are more favored towards your dominant class, in this case coniferous. We're going to talk more about class imbalance when we get to the model evaluation section. Okay, moving on to deriving biomass measurements. So here we are using the individual tree level measurements of DBH combined with the Canadian National Above Ground Biomass equations from Lambert et al. 2005. This paper is linked here if you're more interested in that. So here there are DBH and height allometric equations, but for the purpose of this tutorial, we're just using DBH only equations because not all of the trees in the sample plots have height measurements. So here we have just some code where we're pairing the individual tree measurements with the allometric equations to derive individual tree level biomass. And then here we're looking at a histogram of the range of diameter breast height values, just checking for any potential outliers. We can see that we actually don't have any outliers or NA values in this data set. We have a nice normal distribution. So we can pair for every individual tree in the data set, it will have corresponding allometric equation parameters for different biomass components that can then be aggregated to total above ground biomass at the tree level and then total above ground biomass at the plot level. So deriving total above ground biomass here, we can see some more code examples. We aggregate it to the plot level in kilograms. These can then be converted to tons, and then finally tons per hectare, which is the standard sort of biomass unit that is used in this context. And we can see here we have a histogram showing the distribution of biomass in our data set here. We have about an average biomass, about 120 tons per hectare, ranging upwards of 300 tons per hectare across the full data set. Okay, so moving on to more deep learning specific concepts here. So as Brent mentioned, it's really important in any deep learning workflow that we have these three different data sets. We have our training data set, which is used to fit the model, or in other words, adjust those weights and biases. We have the validation split, which is used iteratively during training to assess whether a model continues to generalize well and determine when a model starts to overfit. And then we have the test data set split, which is kept completely separate during the training process and is used as a way to assess the final model performance. So there are many different ways we can determine or allocate our samples to these three different data set splits. Some modeling approaches might favor k-fold cross-validation, or you might want to perform stratified sampling based on, for example, above ground biomass. In this case, since we have multiple response variables, we just decided to do a random split. Now, this may not be providing us with optimal model performance, but it is sort of a standard, simple approach that we're going to use in this tutorial. But it's important to note that splitting the data sets is a really critical step, and it is worth providing some thought and consideration. And there's lots of literature and examples online of different ways you can do that. So as I said here, we're just doing a random split. So we're randomly assigning 70% of the input plots to the training set, 15% to validation, and the remaining 15% to test. So this amounts to 174 plots in the training data set, 38 in the validation, and 37 in the test set. And then we can see a sort of table here showing these different data labels. So we have our plot ID, the dominant tree type, the above ground biomass in tons per hectare, and then the different data split. So whenever we're preparing our data in this case, I think it's always really important to visualize what these data splits look like, specifically with regard to our response variables. So that's what we're doing down here. First of all, we can actually just look at the spatial distribution of these splits. As Brent mentioned, spatial autocorrelation can be a problem in these modeling approaches, so it's important to just see how these splits are distributed. We can see here, for example, in the southwestern corner of the Saudi area, we don't have that many test samples. That might be a potential area of concern in model assessment. Looking at dominant tree type here, we can see that, of course, we have a very sort of skewed number of conifer dominant plots in our training data set. But generally, we have a fairly even, relative even distribution of our three different dominant tree types across the three data sets. It's important to note that this is a very small data set in the context of deep learning. In the case of our validation set, we only have 5 samples that are mixed plots. And it's important to sort of reconcile this with other deep learning data sets, like, for example, those that are used to train large CNNs, where we might be using millions of images, or in the case of ChatGPT, billions of different text samples. So we're really operating on orders of magnitude less data in forestry, and we're going to talk about this as we proceed through the workshop. In the context of biomass here, we can see that the 3 splits have generally the same range of biomass values. We have about 120 tons per hectare median value for these 3 splits. We can see that, of course, the validation split has slightly more biomass, higher biomass density than on average compared to the 2 other splits. But generally, this is reasonable overlap. So we're going to proceed with these splits. Finally, we're going to look at Z-scoring the above-ground biomass values. Z-score normalization basically converts the biomass values, or any value in this context, to a range using a Gaussian distribution. And the reason we do this is because it helps the model converge faster and more efficiently, because the response variable values, in this case, the biomass values, sort of fall within the same range that these weights and biases parameters might be. So having this normalized distribution sort of helps the model converge more effectively. Now, this is somewhat adds a sort of another layer of logistics, because our predictions from the model will also be in the Z-scored format. So we'll have to convert those back to tons per hectare at the inference stage of the modeling approach. So finally, we have our finished pre-processed data. We have sample plot point clouds stored in this NumPy array format, and that's in this directory if you have downloaded the data. We also have our response variables, that is the data labels for this data set, that are associated with each plot stored in a tabular data set in this labels.csv. And just for context, we can look at one labeled example here. We have a point cloud here, which is conifer dominated. This is plot ID 080, and this has 68.4 tons per hectare of biomass. So this just gives you an idea of what the model is seeing during the training process. Okay, so that is a brief summary of the pre-processing involved. I'm going to pass it on to Yue, who's going to talk about training deep neural network models in the context of EFI.
In this section, I will walk you through how we train deep learning model on the forest point cloud from the pre-processed data Harry just showed, all the way to training models that can classify a dominant forest type and predict biomass. So you don't, at the beginning, I want to mention that you don't need to be deep learning experts or data engineering to follow this. The goal of this workshop is to understand the pipeline well through to run, and also you can modify for your own experiment later. So there are some relevant resources I want to show before we start. So here the PyTorch Lightning is the library we used today for our workshop. So there are official tutorials for your reference to understand how to training loops and logging in more details, because in the workshop today is kept in high level, so we won't go into the very details. And secondly, the DGCN we use in our workshop, here is the paper and the original PyTorch implementation of this paper. And to be mentioned here, the PyTorch Lightning we use today is not the only deep learning in frameworks. There are many other frameworks like the PyTorch and the TensorFlow. So I encourage you to come going to explore these workshops as well. So before you choose the framework in your work, you can explore more. Finally, our demo today is based on the PyTorch Lightning, but and then we use the DGCN as our deep learning framework, deep learning model, and working on the classification and regression tasks. And here is our source code available on the GitHub. Here I can show you a bit. It has some subfolders. Here the dataset folder, you can see we have the data module and the dataset, and also the models here. We implement different models, not only the DCN, for example, the PointNet OCN, and you can easily extend your work, involve more models using this source code, and you can also submit issues when you found a bug, or you you don't very clear how to extend your work in. You can also submit questions, and we will reply to you. And later is the pipeline of the deep learning network. Typically, it involves several steps as shown in this figure. So we firstly set a clear task and objective, what we expected of the deep learning network's outcome. And then we can go to the data preparation step, like Harry just demonstrated, that it involves first find the right data set to solve your problem and pre-process it, clean it, and split into training, validation, and testing sets. While model also need to be resilient to minor changes like the cropping of images. You may need to do data augmentation on the dataset, but we won't involve in this workshop. But just let you know, it's an important part of in forestry, because we have very limited training data. So data augmentation can help your model more generalized and robust to different situations of data. And then we go to the modeling part. We first defining what kind of network architecture we want to build to learn patterns from the data. Like Brent just demonstrated, we have point-based architecture, or graph-based architecture, and CNN-based architecture. And then we will also choose the proper loss function, optimizer, and building the training loop. And then we can start training the model and tuning it until it achieves convergence. After the model has been trained, maybe you want to use your model elsewhere, or we need to take it to production, so we can create deployment ready format files that can work in their environment. But this step might be more common in industry, so we not include in this workshop. And all of these steps might sound very overwhelming, but the PyTorch Lightning make it easy to construct the entire deep learning models. It composed of 3 abstract classes. Firstly is the Lightning data module. It standardizes the training, validation, and test splits. And in our and also maybe the data preparation, like the data normalization and augmentation if needed. So in our case, the data module decides which plots go into training, validation, and testing, and how they are batched during the training. And the Lightning module is a class that uses to define the model structure and the inference logic, optimizer and scheduler details, and training and validation logics, and so on. And the trainer manages the whole process, the running loops, how to save in models, and how to log in the results. So that's basically the pipeline of the PyTorch Lightning in framework, and I think now we will go into a 15 minutes break, and then after the break, we will back to go into introduce the details of each module of the PyTorch Lightning and how to use to predict and do the training stuff. Yeah. Hi, welcome back, everyone. Yeah, so yeah, here is a component we mentioned last before. So the first step of deep learning project network is getting your data from file on the disk into tensor on the GPU. So in this deep learning network, we handle this by two Python script. Here, the first one is EFI dataset, and another one is EFI data module. The EFI dataset is responsible for read and prepare the individual plots, and the data module is organize those plots into training, and validation, and test loaders. So specifically, the EFI dataset was taking a single point forest plots from disk and turn it into tensor. First we read the raw files and load the point cloud from the NumPy array that we just processed before, and then also read labels from the tabular table that to read the labels for the classification task or for the biomass regression. And then we sample points into a fixed number of points. And I saw someone just asked how we're handling the density difference in different data sets. So that's basically in most deep learning networks, they will do that sampling in the input to fixed number of points, so that also can reduce the memory required, computational memory, because the original point clouds usually have very large amounts of points. So subsample it also can benefit for that, and also then we compute the operational features, as some networks like the PointNet, they need the surface normal as input. So we can calculate this kind of features, or maybe other features like the RGB or point cloud if you are assembled with the coordinates, and then we stack these features and feed into the memory. And here our specific parameter is configuration is process data. It means when because we have this pre-process steps. So if you want the next time you don't want to process it again, so you can catch the data and reduce the computation time for the following training. And the next is the data module, where the data, the EFI dataset focuses on one plot at a time. The EFI data module focuses on how many plots move through the system together. And here we can scroll down, and here its first job is to create the training, validation, and test sets. So it does this by reading the tabular sheet that Harry just generated, that contains the training and validation and test labels, and so you can read in this table and group the plots accordingly. And next, the data loader will control the batch size, which determines how many plots the GPU processes at one time. And it also manages how many background workers that are loading the data in parallel. This helps the GPU busy instead of waiting for the next batch to be prepared. And then is after we feed the data into the model, so the co-order the system first prepare the data or catch the data if needed. So and then set up the data. Here you can see in the code we have set up the training data set, validation data set, and test data set if we are in the test mode or prediction mode. And then the test loader will load the data into GPU and to the model. So now we have seen how data gets to the GPU. We can first learn how to learn from the data. Specifically, we rely on the EFI module, which bundles everything related to learning into one place. It first defines the model, DGCN in our case, and how the error is measured during the training using the loss function, and how the weights are updated by the optimizer and the scheduler, and how the performance to be tracked using the evaluation metrics. Here we use the DGCN in our demonstration since it's smaller than the state-of-the-art transformer networks, and it's very popular. Almost everyone know it because it's quite efficient to extract the local features using the DGCN. So I will briefly introduce how the DGCN works to you. In DGCN here, we can look at this figure. For each point, it first find a small group of nearby point. For example, in the yellow one is a node, and here is its neighbors, and then it calculates the 8 features between the point and its neighbors, and they agree together to construct this kind of graph. So you can think of this like an ecologist who doesn't just measure one single tree, but constantly re-evaluates how each tree related to the surrounding trees and in that stand. So this allows the model to learn more complex and abstract relations in the data. And for the implementation part, the model is a stack of The model is stack of 4 edge count features. So in each edge count features, it will build a graph we mentioned before and extract features from the local neighborhood and pass these features forward, and then use a global polling to extract the global feature and then stack the feature together to the classification head or the regression head by the multiple perceptron layers. And finally, we will generate the output for example, for the classification, we use log softmax to generate the maximal probability of each classes, and to for the regression, we generate the numbers of biomass as a final layer. And then is the loss function, which tells the model how wrong it is. The loss is a signal that drives learning. Everything drives the learning. So the model training is for minimize the loss at the end. So for the classification, we use negative log likelihood loss. This means the model is rewarded for aligning high probability to the correct class, and then penalize when it's confident about the wrong one. And for the regression, we use smooth L1 loss. This behaves like squared error for small mistakes, which helps us with stable learning, and like absolute error for larger mistakes, which is more robust for the outliers. And for the evaluation, metrics helps us understand performance in a more interpreted way than the loss alone. So for the classification, we usually take overall classes and also per classes accuracy for to show whether the model is biased towards certain forest types. And for the regression task, we use R squared to measure how well the predictions match true values. So the EFI model module typically has four main functions to define how model and loss metrics and optimizers all move through the training, validation, and prediction steps. So here is core functions. The first is the initialize function. When the trainer starts, the function builds everything the model needs. Firstly, it saves hyperparameters and also sets the configurations and also initialize the model. For example, in our here will be DGCN will be initialized here, and then we also initialize the metrics we will use in this different the tasks. And for different tasks, we will use different metrics here. And then is the forward path defines how data flow through the network during inference. In our case, it's quite simple. It's just pass the points through the backbone and returns the model's prediction, and then is a logic hook. Here we define what happens in a single step, and the Lightning will handle the rest logic. You can see here all the training, validation, test, and predict step will share a logic together, which is we define in the shared step, which we first unpack the batch into points and targets. Here is a plot ID we don't need at this moment, so we set it as none, and then we transpose the tensor so it matches what DGCN expects in the right order. And then we run the forward pass, compute the loss, and return three variables: the loss, the prediction, and the target. So here you can see in the training step we just need the loss we calculated, and here in the validation step to be noted here, we also just calculate the loss, but in the test step we will also updated the test metrics to log the metrics and compare later. And here, to be noted here, the test step is the final unbiased evaluation. So this only runs when we call the test function. It typically loads the best checkpoint from the training and evaluates it on strictly held out dataset in case your model is overfitting on the test split instead of on the evaluation split. And for the predict step, we won't calculate the metrics. We just output we just log the model output. So when we want to generate the plot level predictions or export results for further analysis, like generate species maps, we will call this function. And its optimizer and scheduler. This function tells Lightning how the model should learn. The optimizer, like the Adam or SGD or other optimizer like Adam W or other, and there are many optimizers you can use. So for different tasks and also different scale of your network, it will have different options. So I encourage you can explore more on different optimizer and scheduler settings. It will impact the final output or the accuracy of your output. So in this one we use Adam, and for the scheduler we use step R. For the optimizer, it controls how weights are updated to minimize the loss. And the scheduler will control how the learning rates change over time. So the Lightning expect this in a structured format so that it can automatically call the scheduler at the right moment. Here is optimizer and learning scheduler in this kind of structure. And after we define what's happening in one batch in the module, the trainer is the coordinator that coordinating the workflow. It decides where the model should run and when the things happened and what gets saved and logged. So firstly, we have some configurations to fit into the network, like what task we wanna solve now, and also the location of your label and or your data and the classes contained in the dominate for classification task and some other settings. And then we will go to the trainer class. So for so for instance, it will handle first handling in things like the GPU or CPU selections, and I think it should be yes here, and then it will define in the wait, I cannot find it. Okay, it will define the logger we want to use. There are some options like the TensorBoard logger and also the 1dB logger, and also some other options you can see. But for this demonstration, we use the 1dB as our data, the training logger, and also we have defined some callbacks that to watch what's happening during the training and react to it. So the most important here is the model checkpoints that will monitoring the validation metrics like the overall accuracy for the classification task, and also the squared R for the regression task, and also then we will when the for example, for the overall accuracy reach the highest point, the classification the model checkpoint will automatically log the best the weights and the bias in that model and save as the best model. And then we will have we can also monitor the learning rate, and we can set the early stop, as I mentioned. If your data set is quite small, or your network is too large, it's very easy to happen the overfitting problem. But the early stop can, if your network won't improve like in 10 epochs, it will automatically stop the training intermittently. And okay, so when you call the trainer fetch, the lightning will enter loop that repeats for a fixed number of epochs. For each batch in an epoch, it first pull a batch from the data loader and call the models in the training step, and runs the forward path and computes the loss. And but for the PyTorch Lightning, it won't exactly call the loss backwards. It will do it automatically for you, so you don't need these steps in the PyTorch Lightning. But in other frameworks like the Torch, you will need to exactly call these functions to update the parameters of the network, and then record the metrics during training and evaluation. And then after at the end of each epoch, it will switch to the validation mode. It first runs the evaluation step on the validation stage, and check whether the performance improved or not. If it did, the checkpoint callback save the model. So yeah, so that is a logic for the when you call the trainer fate function here. After we start training, we also need to rate the learning curve to see if the model run properly. So we need to find a sweet spot in the deep learning curve. So for example, here are some normal patterns during the training. Here, I'm not sure if it's clear enough. Okay, so here you can say for the underfitting, you can say the error is quite high, although the training loss and the validation loss are quite close to each other, but the performance won't be very good because the loss is still very high. And for the just right one, the training error is slightly lower than the validation. And for the overfittings, you can say the training loss is very, very low, but the validation loss is not stable and has such kind of curves. And to help you understand, you can think when you have overfitting, for example, for the overfitting problem, you can get more data that will become more stable, and also you can perform stronger regularization on the network, and reading these curves can help you set the network more properly. And to monitoring the learning loss, we use weights and bias tool. Here you can see some. Here we have set the NDB logger and the path where we want to store, and also here is some example of the you can monitoring here. For example, the solid line is training loss, while the dot line is the validation loss. You can monitoring the loss during the training in real time. And another part is the hyperparameter tuning, because we find the learning, for example, we find the learning curve is not very good, so we want to try other hyperparameters like the learning rate and batch size and even the layer depth and width, so on. So we first train a deep learning model, and then we use the validation set to access the performance, and then if it's not very good, we adjust the hyperparameters and we retrain the deep learning model, and until we find the optimal hyperparameters. And some very common strategy should be the random parameter search, and also some great hyperparameter search and so on. But when you getting more familiar with the deep learning training stuff, you will find you can first follow the state of the art settings, and then slightly adjust these parameters a bit, so it won't be a very big problem for you. And here again, we can use the 1DB to monitoring in the result. For example, here for the batch size, we test the batch size and the learning rate, these two hyperparameters, and here you can easily find which one performs best with the validation set using the overall accuracy to monitor. And here you can see when you stop here, you can see the best one is the batch size with 16, and also it can also export something more hyperparameters to compare different hyperparameter settings, like the running time, the steps you run, and epochs you run when training. So I think that's basically what we for the training a network, how should we training a network. And another important is after you trained a network, you can do the prediction on your test data, test stability, and here is you can also do the prediction step. And here you can see the output. We output a tabular table, and here, for example, for the dominant species classification, we have the ground truth and predictions. You can compare it, and also for the biomass. But how to use this output, we will further introduce in the next session by Harry and Brent. And the last piece of practical information is how to run the source code for your work. So again, here is the how to set your environment. Basically, we use UV as a package container that is very easy to set the environment, Python environment. And for training, you just set the model name like DGCN and also other hyperparameters and the logdr. And for the testing, another configuration is the checkpoint path. You use the best performed check weight and bias as your log model and use it for the testing. Yes, yeah, I think that's all for the training models part. And I'd also love to hear how you are thinking about applying this pipeline in your own work. And I think we will be very glad to help you in set your own pipeline and in data preparation, model choice, and so on. So, yeah, I will pass to Harry and Brent for next session.
Thank you so much, Yue. And I think that's a great introduction into just starting to understand what's going on within these models. I'm going to quickly share my screen here for this next component here. So now that we have trained these deep learning models and we have this prediction, we can start to understand these different evaluations and how these models generalize to different data sets based on the testing data set that we have. And again, this is a completely separate data set that we are using that is separate from the training and the validation. So that way we can understand the true model parameters that we have learned throughout this process. And so this process, we have already done the logging of the loss, but that we want to go beyond that. We want to understand what is going on within these data sets. We want to understand how these models are predicting these different variables. So we're going to use that with the prediction and the target. And these are super, super important metrics to kind of understand. And so as we move forward, we're going to have these different classification and regression metrics. But what we're going to really focus on here is understanding and visualizing our predicted results. And so one thing to note is that we do have these predictions on our GitHub page. So you can follow these links to get those different predictions. So that way we can understand what's going on within these data sets. So for tree species classification in particular, what we're going to need to do first is we're going to need to load in our different libraries. So the scikit-learn package has the suite of load in all of these metrics, and we're able to load in all of our predictions, and then we can start calculating these different things. So as we can see for tree species classification, we have calculated these different metrics such as overall accuracy, Cohen's kappa, and F1 score. And we can see that we are around the 90% range for all of these different metrics, which means that our model is doing fairly well. But we can also go a little bit more into detail beyond what's going on in these overall metrics and start to calculate these class-specific metrics as well. So that way we can understand if there's one class that's being dominated in our predictions, or if there's another class that's not doing so well. And so we can do things like these per class metrics such as precision and recall. We can also calculate F1 score for these individual classes as well, so we can understand where our model might need to change a little bit in order to predict these underrepresented classes. We can also plot a confusion matrix so we can see what's going on within these data sets, and we can see that we have a fairly good accuracy for deciduous species and for all of the species. But don't forget, we have a very limited training data or testing data set for this model. So we might want to include more testing data to actually ensure that the representations that we're seeing within our generalized model is actually representative of the entire landscape. Beyond just looking at the accuracy metrics, we can also visualize these different point clouds as well. And so across the top bar here, we can see that we have these classes that are these samples that were predicted correctly. We have a coniferous example, a deciduous example, and a mixed example. On this bottom row, though, we can start to see that, there's some differences that we see from the classified prediction value versus the observed. And we can start to maybe understand, in this first example, it was predicted as mixed, and that might just be because we have this taller tree here with some growth going on over here that might not actually be representative of a mixed plot. or of a coniferous plot. It might actually be some deciduous in there, and we need to adjust our parameters and our modeling approaches maybe to help predict these samples better. Same thing goes for all of the other classes as well. I'm going to pass it off now to Harry to talk about the biomass regression evaluation. But yeah.
Okay, so sort of evaluating our biomass model in this case is somewhat different. First off, because this is a regression model, but secondly, because this is a more complex modeling task. So in our previous example discussed by Brent, we basically have 3 different classes that we're trying to train our model to classify. But in this biomass regression space, we have a sort of continuous prediction space that we're trying to regress. So this is a more challenging task. So the first sort of step in evaluating this model is we need to load in our predicted values, which if you remember from the data processing section, these values were Z-scored. So the model is trained to predict biomass in this normalized Z-score format. So what we first need to do, which is shown in this code chunk here, is to convert the Z-scored predictions back to the original biomass value, which is tons per hectare. So we read in those predictions from the DGCNN model, convert them to tons per hectare, and then we can compare that with the ground measurement true biomass values to get an idea of our regression model performance. So down here we have a classic observed predicted scatter plot showing the model performance. We can see the model fit was not very good. Especially for a biomass model trained using airborne laser scanning data, we might expect better performance in this case. So we have about 68% of the variation explained in the data, and a relative or a root mean squared error of 35 tons per hectare and a bias of 14 tons per hectare. So even with hyperparameter tuning, which Yue described, selecting the best model based on the validation performance set, we can see that when applied to the test data set, DGCNN did not perform quite as well for biomass regression compared to that 3 dominant species type classification. So we could just end the workshop here and move on, but I think it's interesting to look at how we can sort of improve model performance in this case. And I think there's an important lesson here in that DGCNN is just one model architecture among over 100 point-based deep learning models. So it's really important to consider that given architecture might not be the best suit for, or the best fit for your modeling task. So the other important thing to remember is that because this is a more complex modeling task, it may simply be the case that we need more training samples to achieve good model performance. In this case, the Petawawa data set is quite small, only about 249 samples. So the first step we're going to try in this model evaluation phase is to sort of take a step back and say, okay, what if we tried a different deep learning architecture? Now, obviously, Yue only covered the dynamic graph CNN architecture, so I'm going to introduce another architecture here that you can go and read about in more detail separately. But basically, we want to expand this analysis to look at deep learning architectures that might be better suited for biomass. So tree species, you might think has the sort of point-based pattern recognition is more important for understanding structural differences between different tree species, but biomass is more of a volumetric-based regression task. So we have to sort of adapt a model that is more well-suited to that. And there has been several studies published on this concept over the past 7 years or so, looking at how we can apply 3-dimensional convolutional neural networks to regress forest above ground biomass from airborne laser scanning data. So we have one example study from Umke et al. 2024 here, which was done in Denmark using a large data set of over 6,000 plots. And they applied this sparse 3D CNN, among other deep learning models, to estimate forest above ground biomass. And what these authors found is that this sparse 3D CNN actually outperformed the point-based models. So this is what we try to follow in this follow-up sort of example, building on DGCNN. We don't implement the Minkowski engine model that was from this study, but we implemented a model that we investigated in our lab, which we published a paper on in 2023 called Octree CNN, which performs similar depth-wise convolutions on not a voxelized format, but an Octree data format, which is quite similar to the voxel data. And that publication is linked here. And so when we applied this Octree CNN or OCNN model, we could see that this architecture performed better than the dynamic graph CNN out of the box with limited hyperparameter tuning. So now we have 71% explained variation, about RMSE of 34 tons per hectare. So you see, selecting a different architecture did provide us with improved model performance. But how can we take this further, though? So as Brent mentioned, there is this technique called transfer learning, where we can take a deep neural network, in this case OCNN, that was pre-trained on a larger data set, and then fine-tune it on a smaller data set, in this case the Petawawa Research Forest data set. So because we had performed this study back in 2023, we actually already had a pre-trained Octree CNN model, and this was actually trained using the New Brunswick Provincial Forest Inventory. And from this inventory, we were able to use over 2,000 sample plots to fit this original Octree CNN model. So what we've done in this example was we took that pre-trained Octree CNN and then fine-tuned it on the Petawawa Research Forest dataset. What we found was that we actually achieved much better model performance, improving our explained variation by more than 10%. Sorry. We were able to improve our model performance by over 10%, achieving root mean squared error of 29 tons per hectare and a much lower bias of 1 ton per hectare. So to summarize here, we sort of initially tried to apply DGCNN to biomass regression, found that the model did not perform quite well, even with hyperparameter tuning. We then opted to select a new architecture based on previous research, and that was OCNN. And then we further improved that architecture performance by implementing transfer learning. So these were just two sort of strategies we explored in this example to improve DNN performance. But there are many other strategies you can take to improve model performance. And I think this is one of the key things of deep learning, is that the complexity of these models is both a blessing and a curse. It means that these models are very prone to overfitting. A given architecture might not be well suited to a given task, but it also means that the training strategies we can implement are very diverse, and these models can be manipulated and tuned and tweaked to fit different objectives. So I've linked, so there's a couple other things we could have done in this case. We could have performed more rigorous hyperparameter tuning, perhaps using Bayesian optimization. We could have performed more data augmentation to increase diversity in the data set, as Brent mentioned in the introduction. Or we could explore some ensemble modeling techniques, or we combine, for example, we combine DGCNN with Octree CNN or other different models. And there was actually some good points about ensemble modeling in the webinar yesterday in the context of EFI. So I've linked this study by Safanova et al. 2023 here that actually provides this useful flow chart for how to address this small data problem in forestry and remote sensing. And in this case, we just used one of the solutions here, which is transfer learning, but there's many other modeling strategies that are provided here. So if you are trying to implement point cloud deep learning for your own work case, I strongly recommend you read this paper or check out this flow chart, because it might provide some useful direction for what modeling approach to implement in your situation. So I think the question that we're all wondering right now is, okay, well, these deep learning models perform quite well, but how well do they perform compared to a conventional modeling approach used in an enhanced forest inventory? So in this tutorial, we actually have a sort of separate section where we train and develop a random forest model, which I've linked here. So we're going to check out that page really quickly. So here we just used the classic approach of deriving LiDAR metrics at each individual sample plot and then fitting a random forest model for both dominant species classification and biomass regression. And I'm not going to go into the code because this is probably an approach that many of you are already familiar with, but I think it's important to note that this whole random forest modeling approach is summarized in this one relatively short notebook, which is considerably shorter than the large amount of code used for developing the deep neural networks in this example. So just food for thought. So below we have a comparison of the random forest model we developed versus the DGCNN model for tree species classification. And we can see that DGCNN outperformed random forest with only 3 misclassified plots versus 9 misclassified plots in the case of random forest. So in the context of this 3-class classification task, we can see that the deep learning approach performs substantially better. If we move on to biomass regression, we can see that the random forest model achieved an R-squared of 0.74, and the transfer learned Octree CNN outperformed this case by about 5% additional explained variation with an R-squared of 0.79. But if we reflect back on our first implementation of dynamic graph CNN for biomass regression, we can recall that that had actually a worse model fit than random forest with an R-squared of 0.68. So the take-home message here is that if we're just applying a model, out of the box, it's likely that random forests or other simpler approaches are going to perform better. And these deep neural networks will often require somewhat more effort to sort of get substantially good performance out of these models. But I think as research progresses and as software improves, we're going to see it become increasingly easier to implement these models and get strong initial performance on these data sets. Finally, in this model evaluation page, we've also provided some more examples of different point-based deep learning models. For example, PointNet, PointNext, and how different hyperparameter combinations like different batch size and different learning rate affect the validation performance. So I think this is all for both biomass regression and classification. So this is another just interesting thing to look at about how big of an effect these hyperparameters can have on model performance. Okay, I'm going to pass. So we're going to move on. We're going to move on to the final section of the presentation here, where we're going to talk about some examples of deep learning models applied for EFI from the research of Yue, Brent, and I. So in this, oops, I think I'm on the wrong window here. Okay, so in the case of these examples, we're going to discuss 3 studies that were published over the past year or so. And all of these studies were performed in the Romeo Millet forest. So we have sort of a consistent study area here. And the point of these 3 studies is just to sort of demonstrate the benefit we can achieve by extracting information directly from point cloud data using the aforementioned deep learning approaches in the context of EFI. So I'm sure most of you are familiar with the Romeo Millet forest. This is a sort of another sort of remote sensing, primary remote sensing forested area in Canada, where we have really, really high quality LiDAR and plot data. This is a boreal forest type located near Timmins, Ontario. So the first study we're going to talk about, this was some work that we did back just recently, and the paper is still just in the process of being published right now, but should be available within the next month or so. Now, this was another paper where we looked at how to address this small data problem in the context of forest above ground biomass regression in a deep learning context. So in this case, we're not simply regressing total above ground biomass, but we're also looking at individual component biomass. So, and these were derived from the Lambert et Ung national above ground biomass equations. So we're looking at wood, branch, bark, and foliage. Now, while total above ground biomass is typically a more common EFI attribute to model, these sort of different biomass components can serve different information needs, for example, being used to quantify fuel types or for forest residual biomass harvesting, potentially being used in bioenergy applications. So the Romeo Millet forest has a similar size to the Petawawa Research Forest dataset. It has 244 fixed area plots that were sampled in 2019 with airborne laser scanning data collected in 2018. This dataset had a point density of 40 points per meter squared, with total and above ground biomass calculated using allometric equations in a very similar way as was demonstrated in this tutorial. So we use this aforementioned octree CNN architecture that I sort of described in the previous section. This was developed by a researcher who worked for Microsoft, Wang, in 2017. And we've used it in a couple previous studies here. So the octree CNN performs these depth-wise convolutions on multiple resolutions of the point cloud data in this octree format. So it sort of works similarly to a sort of 2D CNN, but on a 3D space. And in this modeling approach, we use this self-supervised learning workflow to sort of help overcome the limitation of not having a sufficient number of samples to train a deep neural network. So self-supervised learning is a deep learning training strategy, one of the previous strategies that I mentioned in that list, or that flowchart I showed in the previous section. So self-supervised learning involves pre-training a model given a task that is inherent in the training data. So what I mean by a task that's inherent in the training data is that we don't need to have any data labels. So for example, ChatGPT was trained using self-supervised learning, where the model was given text data, and then different words or strings of text in the data were randomly removed or masked, and then the model was tasked with predicting the missing text data. So we can apply a similar concept in the point cloud space, where, for example, a model could predict missing chunks of point cloud data to then learn general purpose features about point cloud forest structure. And then we could fine tune that model for biomass regression. So in this case, instead of predicting missing point cloud chunks, we actually developed a novel pretext task involving the multi-output regression of LiDAR metrics, which we know are already correlated and indicative of different forest structural attributes like biomass. So we developed a multi-output regression pretext task involving the regression of LiDAR metrics on 500,000 unlabeled point clouds. These are point clouds we don't have any ground measurements for. And this pre-training step provided the model with prior information about forest structure. And then we were able to fine-tune this model similar to transfer learning on the smaller labeled data set for forest above ground biomass component estimation. And so to understand how well this self-supervised learning approach performed compared to traditional modeling approach with both random forest and with this model trained without any self-supervised learning, in other words, trained from scratch, we sort of compared these three modeling approaches. So we can see that the transfer learned octree CNN model, or OCNN fine-tuned, achieved about 82% explained variation on the biomass data, whereas the model trained from scratch only explained about 0.77% of the variation of the data. And then compared to random forest, we can see that there was a smaller performance gain. I think one of the most interesting parts of this study, though, was we actually looked at the size of the training data set on the effect of these three modeling approaches. This multi-panel figure here, we can see that the number of training samples on the x-axis, and then the root mean squared error of those trained models on the y-axis. And we can see that given smaller training data sets, the fine-tuned octree CNN model actually outperformed both random forest and the conventionally trained octree CNN. So we can see in this range of 20 to about 50 training samples, the deep learning approach actually outperformed random forest, which is quite an interesting result given that we typically expect deep learning models to perform poorly given very small training data sets. We applied the fine-tuned model to the entire Romeo Millet forest to get an idea of how this model applies for inference. We can see that we get some nice biomass maps for both total biomass and component biomass. So the key take-home messages from this study are that this self-supervised learning approach has potential to help improve the performance of deep learning models in these small data situations. This approach can also help reduce the computational demands because models can converge faster when they're pre-trained. And then finally, these pre-trained models like octree CNN can be applied for new out-of-the-distribution data sets, for example, like the Petawawa Research Forest, or it could be applied for different tasks like species classification. I'm now going to pass it on to Iwe, who's going to talk about tree species composition estimation using deep learning.
Okay, here I want to share an example of how to use deep learning on tree species composition, which is based on the publication in last year. It's about multimodal, multi-temporal, multi-scale data fusion network for tree species composition mapping. And so firstly, tree species composition is an element that's very important for forest management, and also by identifying the tree species composition, forest managers can implement like sustainable management practice such as silviculture intervention, and we can also for the biologists we can also use it for monitoring forest health and analyze the biodiversity of the forests. And for this research, we use multi-step processing workflow to generate our dataset. So here we use 4 seasons Sentinel-2 imagery of the 2018 Romeo forest, and also the LiDAR point cloud of the Romeo forest. And here you can see with the proposed Sentinel-2 imagery, and we stack the polygons from the forest inventory data. We generate a superpixel of each polygon. Here we aggregate all the pixels inside the polygon to generate the superpixel, and inside of it we randomly sample a plot with a number of 7,168 points in each plot. And here you can see, and also the labels from the forest inventory data are also kept for the 9 common species. So we generate 9-dimensional vectors as the labels of the compositions, and in each one it represents the percentage of the amount of that species count in that stand. And then is the deep neural networks. We define 3 streams deep neural networks that can process this process the sentinel imagery and point cloud, and also their fuse data at the same time. So specifically, we first feed in the sentinel. We feed in the sentinel seasonal superpixels, and also we padding them to the fixed size of tiles and into the UNet encoder, and then we generate a global feature here, and we feed into the decoder part to generate the per pixel predictions of that stream. And for the point cloud part, we also following the similar structure of the sentinel stream that we feed the point cloud into the encoder and generate a global feature and use it to generate the point cloud prediction, also the 9-dimensional vector as the input labels. And for the fusion stream, here you can see we contact the features from different streams, and then we use a multi-level member fusion to fusion the features from different streams and different scales, and then we do the final prediction of the superpixel. And for the loss functions, here we use the sum of each streams. Here you can see the superpixel stream and the point cloud stream and the fusion stream to start together to make the network know all the features from different streams together. And we compare the results with different design choices. So firstly, we only use the superpixel mode, which is just imagery data. We achieve 0.627 in terms of squared R, and for the point cloud mode, which is worse than the imagery mode. But with the fusion mode, you can say the we just use we want for some brief explanation here. For the fusion mode, we remove the multi-level member fusion. We just use a fusion classification head to evaluate the effect of the multi-level member fusion module. And here for the fusion mode, we achieve much better than the point cloud mode, and slightly better than the imagery mode. And we can also see here with the member fusion design, we have we have achieved the best performance over all these settings. And when we compare the single season and all seasons, we also have 4% of improvement in terms of squared R. So we can from this we can also generate the wall-to-wall maps using the 2 leading species like the black spruce and jackpine, and or the summed properties of the rest species. And also we calculate the rooted mean square arrow. Here you can see this area is dominated by the black spruce, and the high arrow areas are many in the areas dominated by the black spruce, and also the, for example, here the remainders who occupy the most in that region. And for this research, I think the best key take-home messages are firstly, we use the superpixel-based method to assign the resolution of the imageries and the point cloud, and we can use it to also aid some context info inside the superpixel instead of a single pixel. And also the multi-seasonal data can help the model learn seasonal variations in the vegetation phenology to enhance the performance. And the multi-stream neural network design can effectively aggregate all the features from different streams to help this task. Yeah, I will pass over to Brent.
Thanks, Yue, and that's a great kind of introduction into this next example here, which I'm going to share. Which is about individual tree species now. We've talked about the species composition component of deep learning, and now going into the individual tree species side, we can understand that these variables are super important for understanding different aspects of and to help decision making of timber supply, carbon estimation, habitat assessment, so on and so forth, right? But these traditional inventories often rely on these manual interpretations and often report species composition at this stand level or at this plot level, which limits their detail and potentially their scalability as well. That information is super important. But if we can get into a finer detail of having this individual tree species component, we might be able to work with that data at a different scale or a different level, depending on the operation at hand. So deep learning methods often provide these super powerful tools for mapping tree species, but again, they require these very large, well-labeled data sets. And unfortunately, field-based data sets of individual trees are very time-consuming and very expensive to acquire and don't typically cover the entire forested area, especially when we're working in such large areas like the Romeo Millet Forest. So with that, we often have this bottleneck where we don't have enough training data to train these models effectively to apply them for deep learning. With these advances that we've seen in ALS data and in deep learning, we can start to generate these automated data generation approaches to help overcome some of these challenges that we see within deep learning for tree species estimation. So again, this study is in the Romeo Millet Forest, and we're using existing forest inventory maps as well as field plot data, and we're using that information to train these models. Within this approach, we did an automated tree level dataset creation, which means that we had this automated workflow that is data driven to segment these individual trees from the ALS point cloud. We used a watershed segmentation approach. Yes, there could have been other deep learning approaches that we could have used, but we wanted to use something that lots of people have already used and that has been proven to be successful in many different areas. The tree species labels for these individual trees were either derived from the field-based measurements for some of the examples, but they were also supplemented with some of the inventory information of these pure stands. So we have these pure stands that are large in size, and we took a random sampling from these of plots from these or of pseudo plots, same size as a traditional plot, and we delineated those trees, and we used those samples that we knew were pure stands as the labels for this data set. This allows us to produce a very large data set of individual trees and allows us to avoid that bottleneck of having to manually delineate these trees and manually label them as well. In addition to that, we also had two types of ALS information that we used within this model. So we actually used the raw point cloud, but we also derived the statistical metrics that we often use within forest inventories already. So that way we can maybe improve the results based on what we see within both these data sets. We can extract information from both the point cloud and from these metrics to improve these estimates. In addition to just extracting information from a single point-based model, we developed this approach that we could switch out these different point-based deep learning layers so that way we can choose which one might be best for our specific data and for our specific approach. But we also tested that we in a way that we can combine this information so that we can improve the representational power of this model so that we can, again, improve the classification of this approach. So by combining the point clouds and the summary metrics, we found that we were able to improve classification compared to using only the point cloud by itself or the point-based deep learning approach. So the top three examples here of the models that we ran, we can see that we had around a 55 to 61% overall accuracy. But when we applied that metrics network to these point-based deep learning models, we also then improved our accuracy and our detection rates by up to 8 to 10%. And this is a super important finding because we need to have that improved estimation to make these models more operational. What we also see here is in this image is that we can see that for the 4 different species that we were predicting, that these models with the metrics network were more confident in predicting those samples as well. So as we can see in this bottom example with black spruce, our model for the multi-branch, which is the dual point-based network with the metrics network on top of that, had a confidence for this sample of 98%. It was 98% certain that this sample was black spruce. But when we didn't have that metrics network included in there, we can see that the same multi-branch approach only had about a 50% confidence that this was actually a black spruce model. So we can see here that including those metrics networks, it improves the confidence that these models are able to predict these different species at. So why does this matter? Why do we need to have these automated generation approaches? Why do we need to include these metrics? Well, it's because we don't want to have to manually interpret across an entire landscape. We don't have the time, we don't have the resources to do that, and we need to be able to have some sort of approach with these data sets that we're already using in these forest management aspects. We also want to ensure that we have this information and it's usable, that it's actually accurate and it's confident in what we're predicting, which is why we're using this information, again, that's already being used in these forest inventories to help us supplement the data that we see within these point-based deep learning techniques. So some take-home messages with this is that ALS can support individual tree species mapping at large scales using deep learning. We can use these automated workflows to help increase the amount of data that we have. Combining the 3D information with this summary structural metrics also improves prediction performance. And then the dual stream deep learning approach that we use within this example also is simple and effective way to combine multiple types of ALS-based deep learning forest information into one standard approach. And so now you're probably thinking, well, how can deep learning change the way that we do these EFI workflows? And as you can see from these examples, and there are many other examples out there, deep learning has proven to be beneficial for using them on point cloud data for forest operation and forest management and inventory approaches. They often outperform conventional methods such as random forest that rely solely on these handcrafted LiDAR metrics. These performance gains are also a huge benefit for the shift to move towards deep learning workflows when developing EFIs. As we start to try to generate these more complex outputs. Species composition. We're not just estimating a single species anymore. We're estimating multiple species and the proportions that we see within them. We're not just estimating just total above ground biomass. We're estimating the biomass of these different components. And these challenging tasks, deep learning is very successful at doing those. It can also work very well with these complex data sets like ALS point clouds that are super hard to work with if we don't start to grid them into these summary metrics. We can estimate these different approaches using the raw point cloud without having to estimate or use different variables associated to them. However, this remains critical that we it remains critical that we weigh these performance gains against the complexity, the knowledge that is required to train these models, as well as the computational demands that we see within these data sets as well, in order for them to be used operationally. As you probably have already learned, sometimes the setup of these networks are very, very complicated. It takes a lot of time and patience to set these things up properly so that way they can be used effectively. And I think this is an important step that we need to take in order to help training. And these workshops that are being provided are just one of the single steps that can be used to help with that. Again, I just wanted to thank every single person that joined this workshop for today, and I also wanted to thank everybody that invited us to do this workshop as well, because I think this is such an important component to transferring the knowledge that we have learned throughout in the research components, so that way we can bring it back into the forest management and to all these other different areas of forestry. I also did want to say, please download and clone this repo. You can use this in the future. You can pass this on to somebody else, and this site will remain open as even after this workshop. Finally, I also want to say, if you have any questions after this workshop, please feel free to report an issue using this button here that you can see on this site, and you will be able to reach out to us as well. You can add us on LinkedIn, you can email us, you can do whatever you need to do to get a hold of us if you have any other questions as well. But in the meantime, I'm going to stop sharing my screen. We do have a little bit of time left. We ran through this quicker than expected, but if there are any questions, feel free to drop them in the chat, or you can raise your hand and we can allow you to speak as well.
I also think I just wanted to add one thing, Brent. I think, as you mentioned earlier, it would be really interesting for us to hear about how anyone participating in the workshop is interested in using these methods for their own use cases. And I think there could be some interesting discussions to be had about that as well. People want to share.
Yeah, thank you so much for that workshop. That was super insightful. A question that I had that I don't know if others in the audience have, in order to boost the type of training data sets that we have access to, I know that airborne laser scanning is more expensive, but a lot of people have drones on hand with LiDAR sensors. Is there any capacity or ability to train your data set with like a drone LiDAR data set and then that help with the other?
Yeah, absolutely. I think one of these common approaches that we're seeing nowadays is these more agnostic approaches where these deep learning models are trained not just on a single data source anymore. They're trained on airborne data, they're trained on drone data, they're trained on mobile data, trained on terrestrial data, and all of them combined can help train these models to predict. There's an example of tree species where they had all of these different data sets all across the globe, and they were able to predict this tree species based on all of these different types of data. It is worth mentioning, though, that a lot of these point-based models, depending on the computational power that you have and the memory that you have particularly within your GPUs, you might not be able to provide all of the points that you see within a drone-based data set or a terrestrial-based data set because it's just way too much data. But there are different approaches that have been talked about in the chat as well about how we can downsample these point clouds, how we can increase the representational power of them. So, yeah.
Fantastic. Well, thank you. That's encouraging.
Now, another thing that I wanted to point out, and it was that the lecture that Dr. Joanne White gave yesterday about benchmarking model performance. I think once we start developing better and more comprehensive benchmark data sets for different forest attributes, different EFI attributes, we're going to be able to more quickly develop and assess the sort of feasibility and the effectiveness and the value of these different modeling approaches. So I look forward to seeing how that sort of develops in the future. There is already a data set for individual tree species classification. I don't know if you want to send the link for that, Brent. So there is that existing benchmark, but it would be really great to see benchmarks for other attributes, like, for example, disturbance or biomass or growth. So I think it'll be really great to see the development of those benchmarks in the coming years.
Yeah, I think another thing to point out maybe is the transfer learning, because we have the benchmark, we have a very different source of LiDAR point clouds, and also even maybe other data set. We can learn from the other data set and then transfer to our target domain and target downstream task is quite important to learn the features from public data set and other modalities, so that we can reduce our data requirement of our own tasks. So that could be also a perspective to thinking about. Yeah.
I mean, that's the end for us, but again, feel free to email us or reach out to us with any other questions that you may have in the future.